Good evening, everyone. Thank you for attending this talk. My name is Raghu Raj Kumar, and I work as a dev tech at NVIDIA. So today, I'll be presenting the MPAS on GPU's performance analysis, basically a more deeper look into what happens behind the scenes on GPUs for MPAS. Most of the work has been done by me and Carl Ponder, who's also a dev tech at NVIDIA. But a lot of people have contributed to these slides as well. The key ones being Sumati Pranay and Rich Loff from NCAR, and the two students are from the University of Wyoming. With that, here is the discussion topics. Basically, I want to start with who our collaborators are and a small group that now deals with GPU work on the MPAS. And then the current status of where MPAS on GPUs is being used and the specs for MPAS. Then delving deeper into the MPAS performance on how the call structure looks like, what are the execution methods, what kind of parameters are needed to execute, and then scaling efficiency for the different components or the different calls inside the MPAS. A little more info on the Halo Exchange efficiency, where we stand with the current work, and then I'll be open up for questions. Current collaborators, basically it's a small group right now. Along with NVIDIA, we have National Center for Atmospheric Research, NCAR, University of Wyoming, whose pool of students have been doing the core development work, the Weather Company and IBM. So these involve the core people who actually modify MPAS for exclusive GPU work. And with that, we have the developers that are actually contributing to MPAS on GPUs are Pranay and Sumati from University of Wyoming, Sina Supreet from NCAR, Brent and Carl from NVIDIA. So this slide is taken from Rich Loff's presentation back at GTC. It basically shows the graph or the global high resolution atmospheric forecasting system, which uses internally the MPAS-A as the regional refinement model for forecasting weather. It's a GPU-based forecast model, and this is the branch, this is the code I would be actually talking about. So a little into what happens in the machine is basically they're running a 15 3-kilometer hybrid resolution, which contains about 24 million cells. They use about 220 GPUs. We will talk about what these integration and radiation ranks mean later, but the weather is simulated for 15 hours, and basically the total runtime is between 3,100 to 3,200 seconds. So it's about what we have the best optimal configuration that runs on the production machine. So most of the talk today would be basically kind of a continuation of analysis of what Rich presented back at the GTC. Giving the MPAS overview, it's a fully compressible non-hydrostatic equations written in flux form. It's the finite volume method on a staggered grid. It's a time integration, explicit time integration method, which uses the third order Runge-Kutta, but it's not tied to. You could actually switch it out to. But this is just an intro slide for those of you who are not familiar with MPAS. The MPAS that is in production is basically a 6.x version. So today, what I'll be talking about for performance analysis, we have used three different clusters, basically 2 of them from NVIDIA, and the software stacks would be basically the PGI compiler 20.7, OpenMPI, and the UCX that sits on top of the MPI to accelerate performance. And then we would be, of course, using Summit, which has a 19.10 PGI compiler, and for the MPI, we have the Spectrum MPI compiler. As far as the modules are concerned, inside the MPAS, we have the dynamical core, we have the convection, the NTK or NATITK, the WSM6 for microphysics, novel land surface model, the YSU for boundary layer, Mon and Abukov for surface layer. There's a gravity wave drag as well, and RRTMG for radiation. The radiation in the MPAS is lagged. The interval for all the performance presented today is 15 minutes, and all results are in single precession. There are 2 modes that we run the MPAS in for today's performance analysis. One is the dry die core, where only the dynamical core is actually executed. And the second one is full physics, which basically means the physics plus scalar transport plus dynamics. All of those are executed together. The data sets, we are limiting ourselves from a coarse resolution of 120 kilometer to a fine resolution of 10 kilometer and everything that goes in between. The number of vertical levels is basically 56. For the hardware side, there are two clusters. One of them is Prometheus, which is the DGX nodes containing the Broadwell plus V100 combo with 8 GPUs per node. And the second one is the Saline cluster, which is the DGX A100 nodes, which has the AMD EPYC dual socket as a CPU with 8 A100s GPUs on the node. And these two are NVIDIA internal clusters. And third one is basically the Summit supercomputer, which is basically the Power 9 plus V100 combo with 6 V100 per node. Coming to the MPAS call structure, so here I'm trying to list out or provide a pictorial representation of what happens. So from the begin time step that you see on the left corner here, so we come in and then the CPUs start launching. Here we have two separate sets of CPUs, as you can see here. One of them we call it as the integration, and one of them is called as a radiation. So there are a number of ranks that are launched under the integration category, and a number of them launched in the radiation. As mentioned before, the radiation is lagged, so it basically executes independent of the integration ranks. So it comes in, offloads MPAS to physics, offloads surface layer, and then does the land surface modeling, NOAA, on the CPU, and then again offloads the boundary layer to the GPU, offloads gravity wave back to the GPU, convection, die-core, microphysics, everything out of the GPU. So these arrows here represent basically what we have as the CPU-GPU context switching. Basically, the CPU offloads off and waits for the GPU to complete and then regains the control back. And then that performs the end of time step. So the die-core obviously is not simple. It has several other routines inside that I've listed here for people who are familiar with the MPAS dynamics. On the radiation side, we just have two calls, which is basically calls the shortwave radiation and then does the long wave radiation, and then it keeps continuing there. The generic execution method here is basically where we have, if you take a CPU, we have the integration ranks that are basically located on the CPUs. And then you can see here that each one of them has a representative or offloaded to GPU. And then we have the radiation ranks that are also located on the CPU, and they run a lagged way on the CPUs here. And then we have dedicating a couple of cores here in order to actually do the OS or IO. The basic takeoff here is that the MPAS actually branches off into two separate ranks, even though we have a single execution. It's a single executable, but can branch into two separate ranks. The integration ranks do their own work. The radiation ranks do their own work. And then this allows us to actually do integration ranks exclusive optimization flags for the GPU, whereas the radiation ranks can have exclusive flags for CPU optimization. And that allows us to actually enable OpenMP exclusively just for radiation. And the other thing that you can catch here is this is a very generic execution method. So you can see that there are already multiple ranks for GPU. So this is MPS enabled. In production, you typically see at least 3 ranks on a single GPU that's running. So we can go as high or as low as we want, depending upon what kind of performance you're looking at. And also this here, the MPS enable helps because the CPU GPU switching gives some small gap on the GPU side, so it helps keep the occupancy rate higher on the GPU side. The continuing on the MPAS execution method, so this is basically where there are integration ranks and radiation ranks. Once we have the initialization, we begin the time step, and both of these sets of ranks begin simultaneously. However, the integration ranks and the radiation ranks have to synchronize periodically. And let's call this N, and N is basically the ratio between radiation to integration time steps. So for the example given below here, N is equal to 10. Again, this slide is taken from Rich's slide back at the GDC. So you can see that the single time steps here, the integration keeps moving on forward. And when N is equal to 10, the 10th time step, the radiation thread would actually synchronize with the integration ranks. And during the synchronization time step, the time tends to be slightly longer because there's actually a communication between the integration and the radiation ranks. Now, having known how we execute the MPAS, it's now time to look at the performance. So how good is actually the OpenACC code that's ported? One thing to keep on mind here is MPAS porting goals was actually for portability, not optimization. So not all of these routines are having heavy GPU optimization. So majority of this was basically, the focus here was to actually expose parallelism for all architectures to exploit, not just GPU. So a couple of ways to measure how well we have optimized this code would be basically we compare and contrast with other architectures which you have done in the past, but most of the times we need optimal configurations for other architectures as well. The other way to look at it is look at the profile data for GPU, which we have presented in the past for a couple of different ways, but again, it changes with data sets and configurations. So today I want to present on scaling efficiency of each routine that we have ported. So the easiest one is the die-core mode. So I want to show you how the die-core actually scales. So you see on the x-axis, we have listed out all the different routines inside the die-core, and the y-axis represents how efficiently it scales. So how we measure this is basically we take the 10-kilometer data set, and we have at least 40,000 points on each GPU, and then or higher. And then we measure by increasing the number of GPUs and seeing if the time taken to actually execute that particular routine comes down sufficiently enough. So we have done this for points between 120,000 points per GPU all the way up to 40,000 points per GPU, and the average is presented here. For most of these, you can see that average scaling efficiency is at least 90%. They all have more than 90% scaling efficiency. Acoustic step is actually performing a lot better, but we haven't actually gotten time to analyze that yet. But the other trick here is that each of these routines are called a different number of times inside the die-core. So what you see as the total time there is basically where we actually proportionately scale it and then compute whether we are achieving efficiency on the total time of the die-core. In this case, we are able to get 102%, which basically means we're scaling effectively on the die-core. The second part here is basically looking at the everything else, which is basically physics and scalar transport. And when we talk about the physics, we need to be specific. So we have the radiation 15-minute interval. The number of integration ranks is 20. The number of radiation ranks is 20. So this is SMT equal to 4 and OpenMP enabled. So here you can see that the efficiency is a little lower because we basically poured physics with a focus of actually volume. We are looking at 5,000, 7,000, 10,000 lines of code for each of these different modules here. So the aim is to actually port it faster. Also, the important key factor to note here is which of these actually is most dominant or less dominant. For example, gravity wave drag is just a few lines of code, a few hundred lines of code, and it also has very less exposed parallelism and also takes very less computational time. So we spend less time on it as opposed to microphysics or any other routines. So when we actually, again, scale it by the number of times they are called, then you can see that, again, the total time comes about 90%. So in this case, it's 93% scaling efficiency, which basically shows that we have done a reasonably good job of actually maintaining OpenACC code on the GPU architecture. And here is how it looks like for the overall. So when we see the scaling efficiency to be so good for all routines, we would expect the overall speed up to be significantly good. However, there is this particular pie chart shows why we don't get a much higher speed up. The reason being here, you can see the Halo exchange takes 43.74% of the time. So this particular breakdown is basically for a 10-kilometer data set. Again, radiation interval to be 15 minutes. We have a 10% deviation on the radiation synchronization time step, which is the DTR, which is still acceptable. And the radiation is actually OpenMP optimized, so it actually performs significantly better in this case. So, but still, the Halo exchange seems to be the big chunk. The die-core, on the other hand, seems to be the second largest chunk, 32.2%, and the physics takes about 24. For people who are interested in understanding which component inside physics and which component inside die-core, there's a slide of this graph with the routines after the thank you slide, so you can look at it later. So the Halo Exchange is basically the next place where we are working on to optimize and gain better performance. So the original Halo Exchange was written such that we have about anywhere between 117 to 136 Halo Exchanges for every single time step. So the way this is written is we pick one variable and then we pick one neighbor, we pack that variable, send it to the neighbor, and then the receive is basically the same thing. We basically say one variable, one neighbor, unpack, and keep going. So this basically causes a lot of volumes for Halo Exchange to go through, which is why we see the 44%. Current version, where we are rewriting it, is where we actually say for each neighbor, pack a set of variables and send it to that particular neighbor. So which is way more efficient in doing so. However, the current version, we're not able to do it for all of the 117 Halo exchanges. We're only able to do that for a limited set without actually modifying the core code inside MPAS. So the new version actually brings down the total number of calls from anywhere between 117 to 136 to a maximum of 75. So this basically allows us to get 50% reduction, almost 50% reduction in the number of calls itself. Apart from that, the new Halo Exchange also kind of provides a better looping structure and hence a better exposed parallelism, providing anywhere between 2 to 5% optimization depending on the number of neighbors it's supposed to do. It's supposed to actually transfer the variable to. So one thing to note here in the original Halo Exchange is basically that the overhead on the GPU is where we are launching so many kernels. So we are basically bound by that. So when we reduce the number of Halo Exchange calls and when we actually expose better parallelism by having better loop structures, it actually brings that overhead down. So our preliminary tests, which I'm not presenting today, have shown that there's a 20% decrease in MPI time for 10 kilometer dry die core module. So basically what that means is this number, 43%, you can expect anywhere between less than 30% when we actually present it the next time. So, and the next important exciting thing is that the Ampere can actually pack higher number of points. So it actually provides a better surface to volume ratio. So we would get a better and better performance on the newer architectures. Talking about Ampere, here is the comparison between Volta and Ampere weak scaling curves for dry die core. So you can see that all the triangles are basically the Volta architectures and all the circles are basically the A100 and the colors represent the simulations they're running. This is inside a single node, so it's not actually doing any communication between two nodes, so it's all intra-node communication. So you can see that you're getting anywhere between 1.6 to 1.8x speed up between Volta and Ampere architecture. And the other interesting thing here to note is that this code has not been modified, meaning to say it's out of the box. The same code that we actually wrote for Volta works for Ampere as well in this case. And some of the portions inside the die core, when we create GPU-specific variables, we have done what you call as a performance tuning to work better on Volta, and those seem to still hold good, or maybe we can make it better on the Ampere, but this has not undergone any performance tuning for A100 at this point. The other thing to note here is that we're also able to run 160,000 points on the Ampere for running a dry die core, which is a little tricky to run on V100, especially if we want to run the full physics models. But this is something that we can run with these on the A100 due to the higher amount of RAM available. Looking at, again, the intra-node strong scaling, on the A100, we can still see that it's performing significantly better. We continue to see the same 1.6 to 1.8x performance improvement on the Ampere architecture. And not only that, we're also able to actually run the 655,000 points per node on the A100 as well. So that allows us to densely pack the number of GPUs. So, or in other words, when we run the full MPAS physics, unlike the production, which runs 110,000 points per GPU, we would be closer to 250,000 points on an A100 cluster to keep up with the amount of bandwidth it has and the amount of memory it can support. So currently, what we're doing is we are working on the Halo Exchange integration. It's almost complete. We just have to do some testing with the physics, and then it should be available. So we are expecting the results to be available in the supercomputing conference this year. Apart from that, we have porting routine. We are continuing to port routines on the GPU side. One of them is the RRTMG radiation, so that we can do a lagged radiation with the GPUs. OpenACC version of the RRTMG is available for MPAS-6.x. It's actually, it was originally written for WRF by Jeff Adey, and we have begun to adopt that for MPAS. The GPU coupler, in order to exchange the information, is still being is written in progress. Is a work in progress. We're still writing the code, so it might take us some time before we actually see that coming in. The other thing is the Nova LSM is also being moved to the GPUs. This is because the moment we switch for newer architectures, having 250,000 points per GPU and 4 GPUs or 8 GPUs per node basically makes it 1 million points. And continuing to make that work on the CPU would result in Nova being the biggest bottleneck, and which is what we want to avoid. So we did actually try initial setup for doing LSM on the GPUs, but unfortunately, we had to actually see that there were a high number of scalars, which required a higher amount of stack, which basically means we had to increase the stack and reduce the heap, which led to performance deterioration. So we are currently rewriting Nova in order to use stack scalars as and when they come, so that we can reduce the amount of stack required by Nova. But you should still be able to see the Nova LSM ported to GPUs pretty soon. So that's the current work status, and I'm happy to answer any questions you guys have.
Okay, well, thank you, Raghu. And I guess now would be time for you to try to answer the questions that are in your inbox. So.
Yeah, so the first question is, what was the one major optimization, if that was the case, you had to compromise in order to maintain portability? One of the first ones is basically where starting from the time we worked on, the first major optimization we had to compromise on comes from the die core. There were a couple of loop structures in die intent, if I remember correctly, where we could actually get better performance on the GPUs, but unfortunately, refactoring that loop did not allow us to get a good performance on the CPUs. There was also a methodology where combining 2 different routines into a single routine would have gotten us significantly better performance on GPUs, which again, we couldn't do because when we tried it out, the CPU performance was not that good. Other than that, coming to the Halo Exchange, of course, the one Halo Exchange that we had to compromise, not because of portability, but because of keeping the MPAS code in structure or in shape, was the Halo Exchange. Ideally, the Halo Exchange, we would like to rewrite in a way where we combine and do a multi-variable Halo Exchange everywhere possible. And right now, that's not something that we can do. So that's, in my opinion, if you want to put it in an ascending order, that would be the biggest optimization that we have lost, because we want to maintain the portability with the previous versions of MPAS. So the second one, slide 6, it says radiation interval was 15 minutes for all considered resolutions. Shouldn't it vary with the resolution? So yes, it does vary with all the different resolutions. However, I have not presented MPAS physics runs for anything other than 10 kilometer. Anything that you see as 30 kilometers or 60 kilometers or 120 is pure die core. And for the dry die core, the radiation interval doesn't exist. So in that case, that still holds good. So the second one, what is the breakdown of the 1.6x speed up from the A100 with respect to memory bandwidth could occur? Actually, I do not know the answer to that. We have been, Carl and I have been pretty busy trying to get the MPAS physics numbers, that we haven't actually focused on the breakdown with respect to memory bandwidth and CUDA cores. So that's something I think we really need to do and understand which one is actually facilitating more. And hopefully I can get that to you in the next presentation, yes. Another question about MPAS-A version used in production by weather company. Which framework is used for data assimilation? I think I'm not the right person to answer that. I think Todd Hutchinson, who's the director there, he's a better person to answer. I'm not. I do not want to provide the wrong answer for this. So